We're going to talk about second order systems now. We talked about first order systems when we talked about first order plus dead time approximations. Second order systems are like the next extension. Instead of one derivative, you could think of a first order plus dead time equation as being everything from here on. But now we take into account this second derivative as well, and how that second derivative relates to the first derivative, as well as the process variable itself, and the rate of change, which is determined by the gain and our input. So we have that second derivative there that changes things, but it allows us sometimes to approximate systems better. So we have four unknown parameters. We have the gain, the damping factor, the second order time constant, as well as our dead time. So let's talk about how we see this in a couple different domains. In the Laplace domain, we divide out that u that we see here, and then we get everything in the form on one side, so that we get the form right here. You'll notice that in the Laplace domain that we, going back and forth, you'll want to be able to recognize that, that form we have there. In state space form, what we'll do is we'll have a derivative and then a derivative with respect to that derivative. So dx dt is equal to x2, and then dx2 is plugged into the second equation where we have everything else. And that's so that we can have a derivative, that derivative of the derivative will enable us to get the second derivative. It's similar to what we've done before when we have second order systems. We'll do a coupled system, where we have first derivatives of one system being equal to some output. You see that here, and that output, derivative of that output being used in the second system. So here we can see the second derivative is equal to 1 over tau squared minus 2 zeta over tau s times x2, which is equal to x2, the first derivative, plus kp over tau squared u times the dead time. So that simplifies to this form right here as well. So we have our state space form right here, where we have right here the derivatives changing, right here the states. So think about the process gain. The process gain, and similar to before, is the output divided by, or the delta output I should say, divided by the delta input. And both of those are at steady state, both initially and finally. And we look at the difference there. The damping factor is something new. Our system can be overdamped, critically damped, which is, didn't mean to do that. Critically damped, where zeta is equal to 1, and underdamped. And each one of those will change what our analytic solution is. If it's overdamped, our analytic solution to the response of a step response of magnitude m would be this equation right here. If our system is critically damped, because zeta is equal to 1, we can simplify some of the things up here, and we get this analytic solution. If we're underdamped, and so zeta is less than 1, but not greater than or equal to 0, we have this analytic solution. And those are there for your simplicity. We also have the second order time constant. An overdamped system may be a combination of first two order systems, as we see here. And so when we combine those systems together, you'll note that, as similar to before, when we had two systems, let me just draw it out. If we think back to our transfer functions unit just a bit ago, if we had u here, and we went through two processes, this is gain 1, this is gain 2, right here would be like some y intermediate, and right here is y. What basically is happening is we have u times g1 times g2, and you can see that here. Here's the first gain, and here's that second gain. And so that's where we come up with this full gain for the second order time constant. You can see tau p1 plus tau p2, and so we have this those two forms for our equations and for the process time. The process delay, again, is the time it takes for a shift in our manipulated variable to actually be implemented. The time delay takes the form e to the negative theta s in the Laplace form, Then we have our step function and the offset of that, that function in the time form. So it's just kind of some review. It should be fairly similar now from the exercises we've done, but hopefully these concepts make more sense than they originally did when we first introduced the FOPDT system. This is now our SOPDT, our second order plus dead time equation. We'll go ahead and we'll fit our data model to data in the next lesson. This lesson we'll go ahead and we'll simulate a second order system. So first thing we'll do, we'll clear all, close all, we'll get our system ready to go without any complications from previous tests. Well, then we'll go ahead, we're going to specify that we're going to run for 100 time steps, and our points are going to be to ns divided by 5. So we have 5 points per time point. So we're going to go to 20 seconds. We have a process model where Kp is equal to 2, tau s is equal to 1, theta is equal to 0, and zeta is equal to 1. So this is a critically damped system. This is our analytic solution right here. We're going to look at the overdamped step response, the critically damped step response, and then the underdamped step response, actually. And we're going to compare all of them in figure 1. So we're going to loop through and do each of them. So we'll go ahead and we'll run this first section. I'll go ahead, I'll drag over the response. So you can see in our underdamped system we have some oscillation. We'll want to remember that the underdamped systems have oscillation. Our critically damped system goes right from our process output of 0 to 2 without much oscillation at all, and it does still with a decent time, rise time, I should say. And then we have our overdamped system where we have a slower response to our inputs. And our process input here is a change of 1. Let's now just discuss a graphic response real quick. Before we had a pretty simple time for FOPDTs. We had 3 main things. We would look at the gain, we would look at the process time constant, and we would look at the dead time. We're going to have a couple others, so we'll have input and output and 4 parameters as we discussed before. Graphic metrics specifically depend on zeta and tau s are the main ones that we'll have problems finding. And so what we'll do usually is we'll be able to find the gain right off the bat. So we'll find the gain, and then to find these tau s and the zeta, there's a couple different relationships we can take advantage of. So there's rise time. Actually, let's go ahead. I have a figure somewhere. There should have been a figure. All right, I've added the figure here. So we have a couple different values we'll just want to look at and keep our tabs on. I'll go ahead and highlight a few of them. The rise time is going to be a time right here. I'll make a box. It's the time between this delay. So you have the delay shown right here as 2 seconds. The rise time is the time between when we have a start of a response and we rise to the process output level. You'll have the peak time, on the other hand, which is the time between the response, the initial response. That was not what I wanted. Here, I'll go ahead, just draw it with a pen. The peak time is going to be this right here. The time between when we start to have a response and when we reach the peak, that first peak right here. We have the period, which is the timing between 2 oscillations. That's going to be the period. We have the overshoot ratio. And so you'll notice A is going to be the delta Y, if you will, the change in set point between the initial time, or the initial process output, and the steady state process output. So that's going to be A. B is the difference between where our process output is and at steady state and where our peak goes to. So our overshoot ratio is one of the ways we can solve for things. Another thing is the decay ratio. So the decay ratio looks at how much B overshot and C, that second oscillation, overshot. So then we'll take those relationships and we'll look here. We have rise time, and if we had zeta as well as tau s, we could be able to calculate rise time. Similarly with peak time, peak time is going to be a function of just zeta, as well as time peak and tau s. Our overshoot ratio, you'll see right here, is a function of just zeta, so we can use that. If we know the overshoot ratio, we can solve for zeta here. Given an input over an overshoot ratio, in this relationship, we can solve for our zeta. Similarly, with our decay ratio, it's only a function of zeta, so we're able to solve for our decay ratio. Decay ratio also, it's notable, is the overshoot ratio squared. Our period is a function of tau s and zeta. So once we have zeta, we'll be able to solve for our tau s finally. So let's go ahead through this exercise. We're going to graph first a response where we know the outpoints or the outputs. And we're just going to look at these correlations that we see here. So we'll go ahead, in my live editor, I'll go ahead and run this, move this down. This is going to be our general steps to do for an underdamped system. We're first going to find delta y, then delta u, so our change in steady state conditions of the output, change in the input, and calculate the gain. Then from those we'll calculate zeta either through overshoot or decay ratio, and then tau s from the equations for rise time, peak time, or period. So if we look here, what's going on here, we calculate some lens space that we'll use, the default process model. We'll calculate our overdamped step response, and that's from this calc response function, which takes our second order differential equations and returns them both, and then we simulate through given our conditions. And then we'll go ahead and graph it. It looks like here we've got a couple of things going on. So we define our process model, as we said before. We'll rename our parameters. So instead of tau s and zeta, du, ds. And then we have our peak time. Our peak time we're able to calculate using those conditions above since we know them. And then we'll be able to output what the responses are. So let's go ahead, let's look at our graph and our responses. So here we have peak time, our rise time, the delay, period, decay ratio, overshoot ratio, all within this. We have our step input. You'll notice we've done all this within MATLAB, which is kind of cool. You can see how to print the variables. But if we look at the rise time, about 0.8 is what the rise time is. So rise time is the difference between here and that rise time, that point right there. And it looks about 0.8, so that makes sense. Same with peak time. Our peak time is about 1.5, so 3 plus 1.5 is about 4. That makes sense as well. Our overshoot ratio is equal to, since we know the constants, it's fairly easy to calculate all of these. But just looking graphically, we can see obviously this graph is a little bit, I've zoomed in, so that's the problem. So overshoot ratio was about 0.5, 0.6, so we see B's up here. We'll go ahead and click. So 4.5, so 1.5 over, and this one right here is about 2.4, so about 0.6 of the value. That makes sense as well. We have so decay ratio is about 0.4. Makes sense. Overshoot ratio is about 0.6. If we multiply 2 times 1.6, that's where we'd get about that y of about 3.24. So the step change and then the additional portion. And there you go. The only other thing I can think of is the period. So we have x of 4.5 and 7.7, and 3.1 makes sense there. So if we were to do this and calculate the zeta and everything else, what we would do is we would take these constants right here. So zeta, for example, let's think with the, let's do overshoot ratio, for example. Our overshoot ratio, let's just scroll down. Overshoot ratio is 0.62. So if I open my command window, I'll say OS is equal to 0.62. Now we're going to find zeta as a function of overshoot ratio. So zeta is equal to SQRT, I'll make the command window a little bit bigger, square root of ln OS, so log of the overshoot ratio squared divided by pi squared plus, and then we're going to do log of the overshoot ratio squared again. And we've got a problem here. My guess is it's the parentheses not matching up. And then here, instead of ln, we're going to do log. So zeta here is going to be 0.15 according to that. And does that seem right? Well, let's look at our zeta that we know that it is. Zeta is equal to zeta. Zeta is equal to 0.15. There we go. So now let's calculate as if we were doing it the first time. What are tau s? Right here it seems like a good one. I like this one. So tau s is equal to square root 1 minus zeta squared divided by 2 divided by pi times the period. So what was our period? Let's go ahead. We already talked about it. So let's say period is equal to 3.2. Again, we forgot that z was supposed to be divided by 2 divided by pi. So this z was not supposed to be here. One times square root of zeta squared divided by 2 divided by pi times 3.2. So tau s is equal to 0.5. And let's see what we set tau s to originally. 0.5. So you can see how that process works. We'll practice doing that in the next exercise as well.